Fermi Paradox. Imagine for a moment the night sky above you. The twinkling stars are not just distant suns, but potential homes for other forms of life. Given the high probability of extraterrestrial civilizations in the Milky Way galaxy, why have we not yet detected any signs of them? This is the heart of the Fermi Paradox, a question that sits at the crossroads of science and philosophy. The Fermi Paradox questions the apparent contradiction between the high likelihood of extraterrestrial life and the lack of evidence or contact with such civilizations. Named after Nobel Prize-winning physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunchtime conversation in 1950, the paradox highlights the puzzling silence of the cosmos. Here's how it starts. In the vast, unending expanse of the cosmos, where countless stars twinkle and galaxies spiral in the dance of creation, humanity has long pondered a profound question. Are we alone? This inquiry, as old as our own curiosity, has sparked imaginations, driven scientific quests, and inspired countless works of fiction. Our journey begins with one of the most intriguing puzzles in the search for extraterrestrial life: the Fermi Paradox. Our solar system, at approximately 4.5 billion years old, is relatively young compared to the rest of the universe, which is about 13.8 billion years old. Given this, and assuming that interstellar travel could be achieved given enough time, Earth should have been visited by extraterrestrial civilizations by now. Fermi understood that any civilization with a modest amount of rocket technology and a considerable amount of imperial incentive could potentially colonize the entire galaxy within a few tens of millions of years. A blink of an eye in the cosmic timeline. Yet we observe no such presence. This has left astrobiologists and other scientists scratching their heads for decades. Michael Hart, in his 1975 article, An Explanation for the Absence of Extraterrestrials on Earth, suggested that the absence of evidence might best be explained by the absence of other advanced civilizations in our galaxy. He outlined 4 potential explanations. Firstly, the idea that aliens never came here due to a physical difficulty that makes space travel infeasible, possibly related to astronomy, biology, or engineering. Secondly, the possibility that aliens simply chose never to visit us. Thirdly, the notion that advanced civilizations beyond Earth arose too recently to have reached us. And finally, the possibility that aliens have visited Earth in the past, but we have not observed them. In 1980, Frank Tipler, a professor of physics at Tulane University, built on Hart's argument. He proposed that the lack of evidence for interstellar machinery suggested we are likely the only intelligent beings in the galaxy. Tipler's ideas included the concept of self-replicating artificial intelligence, moving from star system to star system, creating copies of itself along the way. The absence of such technology further supported his belief that we might be alone. Today, the topic of extraterrestrial intelligence continues to captivate the scientific community. The discovery of exoplanets, planets orbiting stars outside our solar system, has fueled speculation. The universe is vast and old, with the observable universe being about 90 billion light-years wide and approximately 13.82 billion years old. These staggering dimensions suggest that alien civilizations have had ample time to arise and spread, yet the cosmic gulf between us remains daunting. When Fermi made his famous remark, the only known planets were those in our solar system. However, in 1992, astronomers detected planets orbiting a pulsar, and a few years later, the first exoplanet around a sun-like star was confirmed. Today, over 5,000 exoplanets have been discovered, with more being found each year. This sheer number suggests that life may be plentiful throughout the cosmos. Advancements in telescope technology will soon allow scientists to probe the chemical compositions of some nearby exoplanets' atmospheres. The closest known exoplanet, Proxima b, lies about 4.2 light-years away, roughly 25 trillion miles from Earth. Understanding the habitability of these planets involves more than just finding water. Factors such as the host star's activity and the planet's atmospheric composition are also crucial. Despite the promise of these discoveries, the Fermi Paradox remains. While there seems to be plenty of habitable real estate out there, we have yet to encounter signs of intelligent life. Studies have shown that life might exist in extreme environments, suggesting that microbial life could potentially exist on planets or moons within our own solar system, such as Mars, Europa, or Enceladus. However, the Fermi Paradox concerns intelligent life capable of interstellar communication or travel. To solve it, we need to understand how often life evolves to a level of intelligence and technological capability, and whether such civilizations would desire to communicate or travel among the stars. The premise of the Fermi Paradox is debated among researchers. While some argue that the lack of contact suggests we are alone, others believe the vast distances and timescales involved in space travel and communication are significant barriers. Modern researchers studying exoplanets often use the Seeger equation, an update to the Drake equation, which focuses on finding life that has transformed a planet's atmosphere. The search for extraterrestrial intelligence, better known with the acronym SETI, has yet to find signals from advanced civilizations, shifting the focus to detecting signs of simpler life forms. As we learn more about exoplanets and their potential to host life, we may begin to answer the questions posed by the Fermi Paradox. The vast number of stars in the Milky Way and the growing understanding of habitable conditions will help us make informed guesses about the likelihood of intelligent life elsewhere. For instance, researchers have considered various hypotheses to explain the paradox. One of these is the Great Filter Theory, which suggests that there is a stage in the evolution of life that is incredibly hard to pass. The filter could be behind us, making the emergence of intelligent life extremely rare, or it could lie ahead, posing a significant threat to advanced civilizations. Another hypothesis is the zoo hypothesis, which posits that extraterrestrial civilizations intentionally avoid contact with us, similar to how we observe animals in a zoo without interfering. This could be due to ethical reasons, a form of cosmic quarantine, or simply that they find us uninteresting. There's also the simulation hypothesis, which speculates that our reality is a simulated environment created by a more advanced civilization. In such a scenario, the apparent lack of extraterrestrial contact could be a programmed aspect of our simulation. Moreover, some scientists propose that advanced civilizations might be using communication methods beyond our current understanding, such as neutrinos or gravitational waves, which we have not yet learned to detect or interpret. Alternatively, these civilizations might be focusing their efforts inward, exploring virtual realities or other dimensions, rather than expanding outward into space. These diverse hypotheses highlight the complexity of the Fermi Paradox and the myriad ways we might one day resolve it. Each theory provides a different lens through which we can view the silence of the cosmos, urging us to expand our scientific and philosophical horizons in the quest for answers. Imagine holding 6 tons of sand, each grain representing a star in our galaxy. While it might seem reasonable to think that at least one grain is made of uranium, we don't look for uranium on the beach because it would dissolve in water and wash away. Similarly, just because there are countless stars, it doesn't mean intelligent life must exist around one of them. Current experiments and missions aim to understand the conditions on exoplanets, the likelihood of life, and the potential for technological civilizations to emerge. These efforts will help us better assess the probability of finding intelligent life and the possibility of it spreading throughout the galaxy. The Fermi Paradox remains one of the most fascinating and challenging puzzles in the search for extraterrestrial life. As we ponder the silence of the cosmos, we delve deeper into the theories that might explain this great enigma. In our next section, we will explore the Drake equation, a scientific formula that aims to estimate the number of active communicative extraterrestrial civilizations in our galaxy. The Drake equation. We've delved into the Fermi Paradox and its profound question: where is everybody? Now, let's explore another significant theory in our search for extraterrestrial life, the Drake equation. This equation helps scientists estimate the number of active communicative extraterrestrial civilizations in our galaxy, the Milky Way. The Drake equation was formulated by astrophysicist Frank Drake in 1961. It's not a direct answer to whether aliens exist, but rather a probabilistic formula that outlines the factors we need to consider. Think of it as a way to organize our thoughts about the search for extraterrestrial life. At its core, the Drake equation factors in several variables. These include the rate of star formation in our galaxy, the fraction of those stars that have planetary systems, and the number of planets that might be able to support life as we know it. It also considers the fraction of planets where life actually develops, the fraction of those that develop intelligent life, the fraction of intelligent life forms that develop technology to communicate across space, and finally, the length of time such civilizations are detectable. So, let's break down each part of this equation. First, we have our star, which is the average rate of star formation per year in our galaxy. Recent research suggests that about 1 to 3 stars form in the Milky Way each year. This rate sets the stage for all the subsequent factors. Next, we consider FP, the fraction of those stars that have planetary systems. With the advent of advanced telescopes like Kepler, we've discovered that planets are quite common. In fact, it's estimated that nearly every star has at least one planet, making FP close to 1. Then, there's NE, the number of planets per star that could potentially support life. This is where the concept of the habitable zone comes into play, the region around a star where conditions might be just right for liquid water, a key ingredient for life as we understand it. Studies suggest that there could be around 0.4 to 1.2 potentially habitable planets per star with planets. The next factor is FL, the fraction of those habitable planets where life actually arises. This is one of the most uncertain parts of the equation because we only have one known example of life, Earth. If life is common, FL could be close to 1. If it's rare, it could be much smaller. Following that, Fi is the fraction of planets with life where intelligent life evolves. On Earth, it took about 3.5 billion years for simple life forms to evolve into intelligent beings capable of technology. The factors driving this evolution are still not fully understood, adding another layer of uncertainty. The next variable, FC, is the fraction of intelligent civilizations that develop technology to communicate over vast distances. Here, we consider technologies like radio signals that can travel across space. On Earth, we've been broadcasting radio waves for about a century, a mere blink in geological time. Finally, L represents the length of time these civilizations remain detectable. This could be the trickiest part to estimate. If civilizations quickly destroy themselves or lose interest in communicating, L could be very short. If they survive and continue to broadcast signals for millions of years, L could be quite long. Putting all these factors together, the Drake equation looks like this. N is the number of civilizations in our galaxy with which we might be able to communicate. While the equation itself is straightforward, filling in the values for each variable is where the challenge lies. As our understanding of the cosmos improves, so too will our estimates for these variables. Recent advancements in exoplanet research have provided valuable data for refining the Drake equation. For example, we now know that roughly 1/5 of stars have planets in their habitable zones, regions where temperatures could support liquid water. This helps us better estimate NE and gives us more confidence in our calculations. Astrobiologists Adam Frank and Woodruff Sullivan have taken the Drake equation a step further by introducing what they call the archaeological form of the equation. Instead of focusing solely on the present, they consider the entire history of the universe. They calculate the probability of technological civilizations arising at any point in time across the cosmos, not just those existing now. This approach shifts the question from how many civilizations are out there right now to how many civilizations have ever existed. This broader perspective helps address the uncertainties surrounding the longevity of civilizations and their detectability over time. Frank and Sullivan's work suggests that if the odds of a civilization developing on a habitable planet are better than 1 in 10 billion trillion, then we are likely not the first advanced civilization. This incredibly small probability implies that what has happened here on Earth, the rise of a technological species, has likely occurred many times over the course of cosmic history. Their findings also highlight the impact of recent exoplanet discoveries. With over 5,000 confirmed exoplanets, many of which lie within habitable zones, the chances of life existing elsewhere seem more plausible than ever. These discoveries constrain the value of FP and NE, reducing some of the uncertainties in the Drake equation. However, one significant variable remains elusive: the longevity of civilizations. Human civilization has only had advanced technology for a few thousand years, a mere blink in the cosmic timeline. Whether other civilizations last longer or meet early ends remains unknown. Understanding this variable is crucial for refining our estimates and answering the profound questions posed by the Drake equation. As we continue to explore the universe, advancements in telescope technology and space missions will provide more data, helping us better understand the factors that influence the Drake equation. The quest to find extraterrestrial life is not just about answering a scientific question. It's about understanding our place in the cosmos and the potential for life beyond our world. The Drake equation serves as a framework for this exploration, guiding scientists in their search for answers. While we may not have all the answers yet, each discovery brings us one step closer to understanding whether we are truly alone in the universe. Dark forest theory. We've explored the Fermi Paradox and the Drake equation, but what if the answer to our silence in the universe is far more chilling? Enter the dark forest theory, a concept that offers a haunting explanation for why we have yet to encounter extraterrestrial intelligence. The Fermi Paradox has puzzled astronomers for decades. If the universe is nearly 14 billion years old, why haven't we found any signs of interstellar societies? Why haven't they visited us or communicated with us? The dark forest theory provides a potential answer. They're hiding. According to this theory, the reason we can't see these alien civilizations is that they're all in hiding, fearing potential threats from other intelligent beings. This idea has gained popularity, especially with its depiction in the Netflix series Three-Body Problem. based on the literary trilogy by Cixin Liu. But what makes this theory so compelling, and could it really explain the silence of the cosmos? The dark forest theory posits that the universe is like a dark forest, where each civilization is like a hunter, armed and cautious. In this forest, the primary rule is to avoid detection. Just as a hunter moves silently to avoid revealing their location to potential threats, these extraterrestrial civilizations choose to remain hidden to avoid being discovered and possibly destroyed by others. In Liu's book, the universe is depicted as a place where any sign of life is a potential threat. If a civilization reveals its location, it risks being eliminated by another, more advanced civilization. This is because in the vast, dark forest of the universe, no one can be sure of the intentions of others. The safest course of action is to remain silent and hidden. Unlike humanity, which has been broadcasting radio signals into space for over a century, these alien civilizations have decided that it's too dangerous to announce their presence. This self-imposed silence is a survival strategy in a universe where any contact could lead to catastrophic consequences. However, the plausibility of this theory is a topic of debate among experts. While it is possible that some extraterrestrial intelligences might choose to conceal themselves, it's unlikely that all would come to the same conclusion. Humanity itself is a prime example of diverse behaviors. We have groups that are aggressive, pacifist, curious, and reclusive. If this diversity exists on Earth, it likely exists elsewhere in the universe. Astrophysicist Moya Maktir points out that we don't see uniform behavior even among cultures on Earth. It's improbable that every alien civilization would act in perfect unison, all opting for the same fear-based strategy of hiding. If even one civilization decided to wave hello, it would light up the dark forest for us to see. But anything is possible considering we don't have any evidence of extraterrestrial intelligences to begin with. Perhaps everyone really is hiding. Maybe there truly is a threat lurking out there somewhere in the dark, and maybe humanity just hasn't realized it yet. The Fermi Paradox, first articulated by physicist Enrico Fermi, revolves around the question: if there are so many potential civilizations out there, why haven't we seen any evidence of them? The paradox highlights the contradiction between the high probability of extraterrestrial civilizations and the lack of evidence or contact with such civilizations. The idea that these spacefaring aliens are simply reluctant to reveal themselves has featured in sci-fi storytelling for many decades. Liu, in his 2008 book, gave the hypothesis a catchy name. He describes the universe as a dark forest, wherein each alien society is like a fearful, armed hunter, gingerly moving forth. If that hunter finds other life, another hunter, an angel or a demon, a delicate infant or a tottering old man, a fairy or a demigod, there's only one thing he can do: open fire and eliminate them. In this forest, hell is other people. Being fearful has its evolutionary benefits. On Earth, humans have evolved to be cautious. We may flinch at a strange noise in the night, and although most of the time it's harmless, our caution may save our lives the one time it's coming from a genuine threat. This instinct for self-preservation could be magnified in the vast and unknown reaches of the universe. Seth Shostak, a senior astronomer at the Search for Extraterrestrial Intelligence in California, suggests that being aggressive can have survival benefits. Preemptively taking out the competition can secure resources and safety. Human history is filled with examples of such behavior, from ancient wars to modern conflicts. However, Earth has already announced its presence to the universe. In 1974, the Arecibo message, a radio message containing information about Earth and humanity, was beamed towards the globular star cluster M13. This binary message, aimed at potentially intelligent alien civilizations, was a bold move to communicate with the cosmos. If there are any extraterrestrial intelligences out there within 25,000 light-years, they might have received our message. Despite our boldness, there are significant challenges to the dark forest theory. One major issue is that it is extremely difficult to conceal a technologically advanced civilization. Long before actively searching for extraterrestrial intelligences became a global scientific endeavor, radio signals from Earth's daily communications have been leaking into space. These signals, though weak over vast distances, could potentially be detected by nearby alien societies. Even if an extraterrestrial intelligence tried to conceal itself, it may not be sophisticated enough to work. Some alien societies may have found a way to stamp out all their noise, but others may be accidentally still giving the game away without realizing. The way cavemen might hide is quite different from the way Klingons might hide, says Shostak. The forest analogy also falls apart when you consider the true nature of the universe, or simply our own ginormous galaxy. The woods can seem huge and endless in the dark, but that's peanuts compared to space. There may be hostile aliens out there, says Shostak, but the distances between them are likely to be unfathomably vast. So much so that the idea they would feel the need to preemptively attack one another seems odd, even if they feared each other. The expanse between them means that they wouldn't likely need to compete for resources. Each would have near-limitless worlds, asteroids, and even stars to explore. The fact that Earth is, by universal standards, a young, noisy, and vulnerable technological society, also by default, implies that if there are ETIs out there, then they cannot all be instinctively aggressive. If there are so many civilizations and some of them could destroy us, then we have to explain how that has not happened, says Karim Jabari, a researcher at the Institute for Futures Studies in Stockholm, Sweden. Maybe there's a galactic empire that keeps the hostilities down, or maybe it's really difficult to attack each other over interstellar distances. Or, as Jabari has suggested in a recent paper, extraterrestrial intelligences have reached the same logical conclusion, that they still exist because other advanced alien societies have chosen not to smite them, perhaps hoping instead to have a mutually beneficial conversation. We have no reason to attack them in a preemptive strike, says Jabari. If they're smart, maybe they're thinking the same thing about us, that all extraterrestrial intelligences would share the very human instinct of assuming the worst about an unknown entity is also a massive presumption. For me, the dark forest is one of the less compelling explanations for the Fermi Paradox, because it relies on a few anthropocentric assumptions that I don't think are fair, says McTeer. Fear is a powerful thing, but so is curiosity. That doesn't necessarily mean that the dark forest hypothesis is a non-starter. The problem is that addressing the holes in the theory requires amping up the terror factor. The nightmare scenario is that suppose those that are hiding are right, says Crawford. Suppose that sometime in the history of the galaxy, a technological civilization decided that whenever planets with life or technology were found, they were going to destroy it. In other words, if extermination for extermination's sake was the goal, then the dark forest seems more plausible. If something like that has been going on in the history of the galaxy, then yes, it would explain the Fermi Paradox, Crawford says. So sure, maybe our corner of the cosmos is quiet because life getting started in the first place is an extreme rarity. Perhaps it's lonely out here because alien societies have a bad habit of annihilating themselves once they discover something like atomic weapons. Or, just maybe, we don't see them because they're not there, says Crawford, because a slaughtering entity is going from star to star, extinguishing any sign of life. That's the really scary thing. But let's not forget, the idea of a universe-wide game of hide-and-seek may not hold up under scrutiny. Even if some civilizations are hiding, others might not be, driven by curiosity or a different survival strategy. The diversity of behavior seen in human cultures suggests that not all intelligent beings would choose to stay silent. The last challenge to the dark forest theory is the vastness of space itself. The distances between stars and galaxies are so immense that even if civilizations exist, they may be too far apart to interact, let alone pose a threat to one another. The idea of preemptive strikes or galactic warfare seems more like a plot from a science fiction novel than a likely scenario. Furthermore, advanced civilizations might have developed technologies far beyond our current understanding. They could be communicating in ways that we cannot yet detect or comprehend, such as through neutrino signals or other exotic particles. Our current methods of searching for extraterrestrial intelligence might simply be too primitive to detect these advanced forms of communication. In conclusion, while the dark forest theory presents a fascinating and chilling explanation for the Fermi Paradox, it is just one of many possible answers. The silence of the cosmos could be due to a variety of reasons, from the rarity of life to the immense distances between civilizations. As we continue to explore the universe and advance our technologies, we may one day uncover the true reason behind this cosmic silence. Until then, the dark forest remains a compelling, if somewhat unsettling, possibility. The Zoo Hypothesis. In our quest to understand why we have not yet encountered extraterrestrial life, we come across many intriguing theories. One such theory is the Zoo Hypothesis, which offers a fascinating explanation for the Fermi Paradox. This hypothesis suggests that advanced extraterrestrial civilizations intentionally avoid contact with Earth, allowing humanity to develop naturally, much like how we observe animals in a zoo. The Zoo Hypothesis was first proposed to explain the apparent absence of extraterrestrial life, despite the high probability of its existence. It posits that these advanced civilizations are fully aware of our existence, but choose not to interfere. This hands-off approach ensures that our sociocultural evolution proceeds without external influence, maintaining the integrity of our natural development. One variant of this hypothesis, suggested by former MIT Haystack Observatory scientist John Allen Ball, is the laboratory hypothesis. In this scenario, humanity is part of a vast experiment, with Earth serving as a giant laboratory. Here, extraterrestrial beings might be observing us to understand how civilizations evolve and solve problems like self-destruction, war, and environmental degradation. This concept, while unsettling, underscores the potential altruistic motives of these advanced beings. According to the Zoo Hypothesis, contact with extraterrestrial life might be withheld until humanity reaches certain technological, political, or ethical milestones. For instance, once we achieve interstellar travel or demonstrate a stable global peace, these civilizations might decide that we are ready for contact. Alternatively, contact might occur when we actively seek out these civilizations by sending spacecraft to their home planets. One key assumption of the Zoo Hypothesis is that life, whenever possible, will evolve. Given the vast number of planets in the habitable zones of stars, it's plausible that many advanced civilizations exist. These civilizations, according to the hypothesis, have a deep reverence for the independent evolution of other species. Premature contact could disrupt this natural progression, reducing the diversity of paths the universe could take. The idea of a universal cultural or legal policy among extraterrestrial civilizations necessitating isolation seems plausible. In a universe without a dominant power, random civilizations might make contact. However, a crowded universe with clearly defined rules seems more likely. If all civilizations follow similar ethical standards, it would be easier to enforce non-interference policies. This concept is akin to the Prime Directive, seen in the popular sci-fi series Star Trek, where the Federation avoids interfering with less advanced cultures. However, the uniformity of motive concept faces challenges. It would take only a single civilization or a faction within one to decide to break the non-interference pact, making their presence known. The probability of such a breach increases with the number of civilizations. Yet, if all advanced civilizations have developed similar ethical standards through convergent evolution, they might all adhere to non-interference. This is similar to how various species on Earth have independently evolved eyes. Another possibility is that a particularly distinguished civilization, perhaps the first among them, sets the standards for others to follow. For the zoo hypothesis to hold, these civilizations must overcome significant challenges like self-destruction and resource scarcity, guiding them to adopt responsible behavior. Otherwise, they would likely not survive long enough to become advanced. In this view, no contact would be possible until humanity itself overcomes these hurdles and proves its maturity. One estimate suggests that humanity might be able to test the zoo hypothesis within the next half-century. As we develop more advanced technology, we may eliminate ways in which extraterrestrial civilizations can hide from us. For example, advancements in remote sensing technology could allow us to detect artificial structures or technological activities on distant planets. A modified version of the zoo hypothesis integrates the concept of hegemonic power to explain the Fermi Paradox. The first advanced civilization might establish a non-interference doctrine that subsequent civilizations adhere to. Even if this original civilization no longer exists, its legacy could persist through passed-down traditions or artificial intelligences dedicated to maintaining non-interference. This could explain how a single doctrine could influence many civilizations over millions of years. Despite its appeal, the zoo hypothesis faces significant criticism. Critics argue that it would only take one dissident group within an extraterrestrial civilization to break the non-interference pact. Human history shows that complete uniformity of behavior is rare, and it seems unlikely that all advanced civilizations would adhere to the same policy for millions of years without any breach. Moreover, the hypothesis is seen by some as speculative and more aligned with theological theories than with scientific evidence. One possible counter-argument is that extraterrestrial artificial superintelligences dominate space, including areas occupied by biological intelligences. These superintelligences might merge into a network, dissuading rogue behavior and maintaining the non-interference policy. The zoo hypothesis has found its way into many works of science fiction. For example, in Star Trek, the Federation's Prime Directive forbids interference with less technologically advanced civilizations. This idea of non-interference and allowing natural development is a central theme in the series. In Arthur C. Clarke's 2001 A Space Odyssey, a beacon on the moon is activated when humans discover it, potentially signaling humanity's readiness for contact. Similarly, in Childhood's End, Clarke depicts aliens observing Earth's evolution and only revealing themselves when humanity is about to achieve spaceflight. The zoo hypothesis also appears in more recent works. In the video game Stellaris, players can observe less advanced civilizations without interfering, reflecting the principles of the hypothesis. These fictional portrayals help us imagine how advanced civilizations might interact with less developed ones and the ethical considerations involved. The zoo hypothesis remains a compelling explanation for the Fermi Paradox. It suggests that advanced civilizations choose non-interference to preserve the natural evolution of younger civilizations. This approach reflects a deep respect for the diversity of life paths and the importance of independent development. Expanding on the concept, we can consider the technological capabilities required for such non-interference. Advanced civilizations would likely possess sophisticated surveillance and observational tools, allowing them to monitor Earth without revealing their presence. They might use cloaked satellites, unmanned probes, or other advanced technologies to gather data while remaining undetected. These tools would enable them to observe our technological progress, cultural developments, and even our biological evolution, all without direct interference. Additionally, these civilizations might have developed ethical frameworks that prioritize the preservation of lesser evolved species. Such frameworks could be rooted in a deep understanding of the consequences of premature contact. They might recognize that introducing advanced technologies or knowledge to a developing civilization could have destabilizing effects, disrupting social structures and hindering natural progress. By adhering to these ethical guidelines, they ensure that their presence does not inadvertently cause harm. Another aspect to consider is the potential for extraterrestrial civilizations to communicate amongst themselves, establishing a consensus on how to handle emerging civilizations like ours. This interstellar communication could involve shared protocols and guidelines for non-interference, agreed upon by a coalition of advanced civilizations. Such a coalition could act as a regulatory body, ensuring that all members adhere to the established principles of the zoo hypothesis. The zoo hypothesis also opens up the possibility of a galactic quarantine. This concept suggests that advanced civilizations might intentionally isolate developing worlds to prevent contamination or interference. Earth could be part of a designated no-contact zone, enforced by these civilizations to protect both our development and their own security. This quarantine would prevent any direct contact until we reach a certain level of advancement, ensuring that our cultural and technological evolution proceeds without external influence. Critics of the zoo hypothesis argue that it relies heavily on assumptions about the behavior and motivations of extraterrestrial civilizations. They point out that human history is marked by curiosity and exploration, traits that might be common in other intelligent species as well. If even one civilization decides to break the silence and make contact, the entire hypothesis could be invalidated. Moreover, the vast distances between stars and the timescales involved make coordinated non-interference a challenging proposition. Despite these criticisms, the zoo hypothesis remains a thought-provoking explanation for the Fermi Paradox. It challenges us to consider the ethical implications of contact and the responsibilities of advanced civilizations. As we continue to explore the universe, we must remain open to the possibility that we are being observed, even if we cannot yet detect our observers. In conclusion, the zoo hypothesis offers a unique perspective on why we have not yet encountered extraterrestrial life. It suggests that advanced civilizations might be intentionally avoiding contact to preserve the natural evolution of younger species. This hands-off approach reflects a deep respect for the diversity of life paths and the potential consequences of premature contact. While the hypothesis faces significant challenges and criticisms, it remains a compelling and thought-provoking explanation for the silence of the cosmos. The Great Filter. As we continue our exploration of the cosmos, we come to another profound and sobering theory that seeks to explain why we have not yet encountered extraterrestrial life. This is the Great Filter hypothesis, a concept that may hold the key to understanding the apparent silence in our galaxy. The Fermi Paradox, which we've discussed in earlier sections, asks a simple yet perplexing question. Where is everybody? With countless stars and potentially habitable planets in the Milky Way, why haven't we detected signs of intelligent civilizations? The Great Filter Hypothesis offers a potential answer, suggesting that there is a significant barrier, or filter, that prevents civilizations from reaching an advanced stage of development. The term Great Filter was first proposed by economist Robin Hanson in the late 1990s. Hanson suggested that while life may arise frequently across the galaxy, there exists a barrier that is extremely difficult for civilizations to overcome. This filter could be a natural event, such as an asteroid impact, or a consequence of the civilization's own technological advancements, such as nuclear war. To understand the Great Filter, we must consider the various stages of development that a civilization must pass through to become capable of interstellar communication and travel. These stages include the formation of a habitable planet, the emergence of simple life, the evolution of complex multicellular organisms, and the development of intelligent life capable of using advanced technology. The Great Filter posits that at least one of these stages is so improbable that almost no civilization manages to progress beyond it. This concept helps explain why we have not detected any advanced extraterrestrial civilizations, despite the high probability of their existence. So, what could the Great Filter be? Let's explore some of the potential barriers that civilizations might face. One possibility is that the Great Filter lies in the initial emergence of life. Abiogenesis, the process by which life arises from non-living matter, might be extremely rare. If life is uncommon, then the filter would be at the very beginning of the evolutionary process. Despite favorable conditions, the transition from simple organic molecules to living cells might be an extraordinarily rare event. Another potential filter could be the evolution of complex multicellular organisms. While simple, single-celled life forms might be abundant, the leap to complex life forms that can build advanced technologies might be exceedingly difficult. On Earth, this transition took billions of years, and it required a series of rare and significant biological innovations. The development of intelligence and tool use is another critical stage. While many species on Earth exhibit varying degrees of intelligence, humans are unique in our ability to create and use complex tools, develop advanced technologies, and build civilizations. The evolution of a species capable of such feats might be another significant hurdle. Even if a civilization manages to reach a high level of technological advancement, it might still face existential threats. These threats could be self-inflicted, such as nuclear war, climate change, or the uncontrolled development of artificial intelligence. Alternatively, they could come from external sources, such as asteroid impacts or nearby supernovae. Any of these events could potentially wipe out a civilization before it has the chance to become interstellar. The authors of a recent paper from NASA explore the idea that humanity may currently be facing its own Great Filter. They propose several possible scenarios, including anthropogenic hazards like nuclear warfare and pandemics, as well as natural hazards like asteroid impacts and climate change. They argue that addressing these challenges requires a period of introspection and a collective effort to mitigate risks. Humanity has already survived several significant filters in the form of mass extinction events. For example, the Permian-Triassic extinction, also known as the Great Dying, occurred around 250 million years ago and nearly wiped out all life on Earth. This event eradicated about 96% of marine species and 70% of land species. The exact cause of the Great Dying is still debated, but it likely involved a combination of volcanic activity, climate change, and other environmental factors. However, the current threats we face are largely of our own making. Unchecked population growth, for instance, places immense pressure on Earth's resources and ecosystems. As of November 2022, The human population has reached 8 billion, a significant increase from 1.6 billion at the start of the 20th century. While technological advancements in agriculture and energy production have supported this growth, they cannot indefinitely offset the stresses imposed by an ever-escalating population. Nuclear war remains another existential threat. With the capability to destroy all life on Earth, nuclear weapons represent a significant risk. The proliferation of these weapons and the potential for conflict highlight the fragility of our existence. While there have been efforts to reduce the number of nuclear warheads and promote peace, the danger persists. Pathogens and pandemics are also critical concerns. The interconnected nature of our world makes it easier for diseases to spread rapidly across continents. While advancements in medicine have improved our ability to combat these threats, the potential for a global pandemic remains a serious risk. Artificial intelligence poses another potential great filter. While true artificial intelligence capable of independent thought and decision-making has not yet been realized, the rapid advancement of technology suggests it may be on the horizon. The impact of artificial intelligence on society is uncertain. It could bring about unprecedented benefits or lead to unforeseen consequences. The challenge will be to manage artificial intelligence development responsibly to ensure it does not become a threat. Asteroid and comet impacts are natural events that could also spell doom for humanity. While large impacts are rare, they have the potential to cause catastrophic destruction. The odds of such an event occurring in the near future are low, but over long timescales, the likelihood increases. Initiatives like NASA's DART mission aim to develop methods for deflecting potentially hazardous objects, providing a means of defense against this threat. Climate change is perhaps one of the most pressing issues facing humanity today. The gradual warming of the planet due to greenhouse gas emissions poses significant risks to ecosystems, weather patterns, and sea levels. While efforts to transition to renewable energy sources and mitigate the effects of climate change are underway, the challenge is immense. Failure to address this issue could result in a slow-motion catastrophe that qualifies as a great filter. To avoid the great filter, humanity must work together to address these existential threats. This requires global cooperation, scientific innovation, and a commitment to sustainable development. History has shown that collaboration can lead to remarkable achievements, and it is this spirit of cooperation that will be essential in overcoming the challenges we face. The search for extraterrestrial intelligence, SETI, and initiatives like METI, Messaging Extraterrestrial Intelligence, are part of humanity's broader effort to understand our place in the universe. As Carl Sagan once said, in the deepest sense, the search for extraterrestrial intelligence is a search for ourselves. By looking outward, we gain perspective on our own existence and the challenges we must overcome to survive and thrive. In conclusion, the Great Filter Hypothesis offers a compelling explanation for the Fermi Paradox. It suggests that there are significant barriers to the development and survival of advanced civilizations. These barriers could be natural or self-inflicted, and they highlight the fragility of life in the cosmos. Humanity may be facing its own great filter, but by working together and addressing our existential threats, we can increase our chances of surviving and perhaps one day encountering other civilizations. Rare Earth. As we continue our journey through the cosmos, we come to another thought-provoking theory that attempts to explain our apparent solitude in the universe. This is the Rare Earth hypothesis, which suggests that while simple life might be common, complex life forms like those on Earth might be exceedingly rare. The rare Earth hypothesis was first proposed by paleontologist Peter Ward and astronomer Donald Brownlee in their book, Rare Earth: Why Complex Life is Uncommon in the Universe, published in 2000. This hypothesis offers a possible explanation for why we have not found any evidence of complex extraterrestrial life, despite the vast number of planets in the universe. It suggests that the unique conditions that allowed complex life to arise and thrive on Earth are exceptionally uncommon and unlikely to be replicated elsewhere. Ward and Brownlee identified several key factors that they believe were critical to the development of complex life on Earth. These factors include the planet's location in a favorable part of the galaxy, its stable orbit around a long-lived star, the presence of liquid water, and many more. Let's delve into some of these factors in more detail. One of the most important factors is the location of Earth within the Milky Way galaxy. Our planet resides in what is known as the Galactic Habitable Zone. This zone is not too close to the chaotic center of the galaxy, where radiation levels are high, nor too far out in the sparse and resource-poor outer regions. Instead, Earth is located in a region where there are significant amounts of heavy elements necessary for planet formation and where sterilizing radiation sources are relatively distant. The stability of our Sun is another crucial factor. Our Sun has a long lifespan, measured in billions of years, and it provides a consistent energy output that has allowed life to flourish. Many stars in the galaxy are either too short-lived or too variable in their energy output to support the long-term development of complex life. Earth's distance from the Sun is also just right. We are located within the habitable zone, where temperatures are suitable for liquid water to exist on the planet's surface. Liquid water is essential for life as we know it, and its presence on Earth has been a key factor in the development of complex organisms. In addition to being at the right distance from the Sun, Earth's orbit is stable over long periods. This stability has been crucial in maintaining a climate that supports life. A planet with a highly eccentric orbit would experience extreme temperature fluctuations that could make it difficult for complex life to develop and persist. Another important factor is Earth's axial tilt, which is stabilized by our relatively large moon. This tilt creates seasons and contributes to a stable climate, preventing the extreme weather patterns that could result from a wobbling axis. The moon's gravitational influence helps maintain this tilt, making our planet's environment more conducive to the development of complex life. Earth's solar system also benefits from the presence of massive gas giants like Jupiter and Saturn. These giants act as cosmic vacuum cleaners, their strong gravitational fields capturing or deflecting many comets and asteroids that might otherwise collide with the inner planets. Without these gas giants, Earth and the other inner planets would be subjected to far more frequent and potentially devastating impacts. The planet's mass is another critical factor. Earth is large enough to retain an atmosphere and support liquid oceans, both of which are necessary for complex life. A smaller planet might not have sufficient gravity to hold onto an atmosphere, while a much larger planet might have an atmosphere too thick to allow for liquid water on its surface. Earth also has a molten core that generates a global magnetic field. This magnetic field protects the planet from harmful solar and cosmic radiation, preserving the conditions necessary for life to thrive on the surface. Without this protection, Earth's atmosphere could be stripped away by solar winds, as is believed to have happened on Mars. Furthermore, the presence of plate tectonics on Earth has been vital. Plate tectonics help regulate the planet's climate by cycling carbon dioxide in and out of the atmosphere, preventing a runaway greenhouse effect and maintaining surface temperatures within a range suitable for life. They also build up land masses and create diverse ecosystems, contributing to the richness of life on our planet. Ward and Brownlee argue that the confluence of all these factors is what makes Earth uniquely suited to support complex life. They suggest that the chances of all these conditions being met on another planet are extraordinarily low, making complex life forms like those on Earth very rare in the universe. The rare Earth hypothesis challenges the more optimistic views that suggest intelligent life is common in the universe. For instance, Carl Sagan often posited that our Sun is an unremarkable star, implying that planets like Earth should be abundant. However, Ward and Brownlee point out that about 80 to 95% of stars are significantly different from our own in terms of size, mass, luminosity, and lifespan. This stark difference means that many stars may not provide the stable and long-lasting energy output necessary for the development of complex life. Moreover, the hypothesis underscores the role of plate tectonics, which had not been widely considered in earlier discussions about extraterrestrial life. Earth is, to the best of our knowledge, the only body in the solar system with active plate tectonics, and this process has played a crucial role in shaping our planet into a habitable environment. Despite the compelling arguments of the rare Earth hypothesis, it is important to note that it only applies to complex life forms. Ward and Brownlee believe that simple life, such as bacteria, is likely widespread in the universe. After all, even the harshest environments on Earth harbor microbial life. However, they argue that complex life, which includes animals and plants, requires a far more specific set of conditions. In interviews, Ward and Brownlee have expressed their hope that future discoveries will test their hypothesis. They welcome new data from observatories like the James Webb Space Telescope, which seeks to reveal the atmospheres of exoplanets in detail. Detecting atmospheric signatures, such as oxygen and chlorophyll, could indicate the presence of life. As Ward has pointed out, any complex, rapidly moving and thinking creatures will likely need significant amounts of oxygen in their atmosphere, similar to how life on Earth operates. The rare Earth hypothesis has faced criticism and challenges over the years. Some researchers argue that the presence of a large planet like Jupiter might actually increase the frequency of planetary impacts rather than reduce them. Others question the necessity of a global magnetic field or plate tectonics for the development of complex life. Critics also point out that the hypothesis may be too Earth-centric, failing to consider alternative biochemistries or forms of life that could thrive under different conditions. Despite these criticisms, the rare Earth hypothesis remains a significant perspective in the discussion about extraterrestrial life. It highlights the unique qualities of Earth that have allowed complex life to evolve and raises important questions about the rarity of such conditions elsewhere in the universe. The rare Earth hypothesis offers a compelling argument for why we might be alone in the universe. It suggests that while microbial life might be common, the specific conditions required for complex life are exceptionally rare. This hypothesis challenges more optimistic views and underscores the unique and precious nature of our planet. As we continue to explore the cosmos and gather more data, we may find evidence that supports or refutes this hypothesis. Until then, the rare Earth hypothesis serves as a reminder of the delicate balance that has allowed life to flourish on Earth and the challenges that might face other planets in achieving the same. Simulation hypothesis. As we delve deeper into the mysteries of the universe, we arrive at a hypothesis that challenges our very perception of reality. This is the simulation hypothesis, which proposes that our entire existence might be an elaborate simulation, much like a sophisticated video game. The simulation hypothesis has gained traction in recent years, thanks in part to the work of philosophers and computer scientists. One of the most influential proponents of this theory is Nick Bostrom, a philosopher at the University of Oxford. In his seminal paper, Bostrom laid out a thought-provoking argument. At least one of three possibilities must be true. First, all human-like civilizations in the universe go extinct before they develop the technological capacity to create simulated realities. Second, if any civilizations do reach this phase of technological maturity, none of them will bother to run simulations. Third, advanced civilizations would have the ability to create many simulations, leading to a scenario where there are far more simulated worlds than non-simulated ones. If the third possibility is true, it means we are likely living in one of those countless simulations. To explore this idea further, let's consider some of the intriguing aspects and implications of the simulation hypothesis. Rizwan Virk, a computer scientist and video game designer, delves into Bostrom's argument in his book, The Simulation Hypothesis. Virk suggests that as our technology advances, we move closer to what he calls the simulation point, the moment when we could realistically create a matrix-like simulation. He draws parallels between the development of modern video games and the potential for creating a simulated reality. One of the key arguments in favor of the simulation hypothesis is the concept of quantum indeterminacy. This is the idea that particles exist in multiple states until they are observed. A famous thought experiment illustrating this is Schrödinger's cat, where a cat in a box can be considered both alive and dead until someone opens the box and observes it. In a simulated reality, this concept could be akin to rendering only what is observed, a technique used in video games to optimize computing resources. In video games, especially those from the 1990s like Doom, developers optimized limited computing power by rendering only what the player could see. This approach significantly reduced the amount of processing needed, allowing for more detailed and expansive game environments. Similarly, if our reality is a simulation, the universe might only render what we observe, explaining some of the strange behaviors observed in quantum physics. John Wheeler, a renowned physicist who worked with Albert Einstein, proposed that at its core, everything in the universe is based on information, a concept he termed it from bit. This idea aligns well with the simulation hypothesis, suggesting that what we perceive as physical reality is fundamentally composed of bits of information processed by an underlying computational system. One of the most compelling aspects of the simulation hypothesis is the statistical argument presented by Bostrom. If advanced civilizations can create many simulations, then the number of simulated beings would vastly outnumber the number of biological beings. This implies that we, as conscious beings, are more likely to be part of a simulation than to exist in base reality. But can we ever prove that we are living in a simulation? This question has sparked considerable debate among scientists and philosophers. Some suggest that there might be ways to detect glitches in the simulation, or inconsistencies that reveal its artificial nature. For instance, anomalies in the laws of physics or unexpected behavior in quantum experiments could provide clues. However, the concept of computational irreducibility, which comes from chaos theory, suggests that some processes cannot be simplified or predicted without going through each computational step. This means that even if we are in a simulation, the complex interactions and rules governing our reality would be indistinguishable from those in a non-simulated reality. Another argument against the simulation hypothesis is Occam's razor, a principle that suggests the simplest explanation is usually the correct one. The idea that we are living in a flesh and blood physical world might be simpler and therefore more likely than the complex notion of a simulated reality. However, proponents of the simulation hypothesis argue that if the underlying structure of our universe is based on information, then a simulation might indeed be the simpler explanation. In an interview with Vox, Rizwan Virk discussed how advancements in virtual reality and augmented reality are bringing us closer to the simulation point. He outlines 10 stages of technology development that a civilization would need to reach to create a hyper-realistic simulation. Currently, we are at about stage 5, which includes virtual and augmented reality technologies. The remaining stages involve further developments in brain-computer interfaces and other sophisticated technologies that could make a fully immersive simulation possible. The idea that we are living in a simulation has also found its way into popular culture. Movies like The Matrix depict a world where humans live in a simulated reality controlled by machines. In the film, the protagonist, Neo, discovers the true nature of his existence and fights to free humanity from the simulation. While this is a fictional representation, it echoes many of the philosophical questions raised by the simulation hypothesis. If we are indeed living in a simulation, what would that mean for our understanding of the universe and our place in it? For some, the idea is unsettling, as it challenges the very nature of reality and our sense of identity. For others, it opens up fascinating possibilities about the nature of existence and the potential for advanced civilizations. There are also philosophical implications to consider. If we are simulated beings, what does that say about our free will and consciousness? Are we merely following a predetermined script, or do we have genuine autonomy? These questions touch on deep philosophical debates about the nature of mind, consciousness, and reality. In conclusion, the simulation hypothesis offers a provocative and compelling explanation for many of the mysteries of our universe. While we may never be able to definitively prove or disprove this theory, it encourages us to think deeply about the nature of reality and our place within it. Whether we are living in a simulation or not, exploring these questions helps us better understand the fundamental nature of existence and the potential for future technological advancements. The Galactic Club. As we continue to explore the possibilities of life beyond our planet, we arrive at a thought-provoking hypothesis: the Galactic Club. This concept envisions a network of advanced extraterrestrial civilizations that have established their own interstellar community. What would it mean for humanity to join such a club? What changes and adaptations would we need to make to our own laws and values? The idea of a galactic club suggests that there is an interstellar community of advanced civilizations, but humanity is not yet advanced enough to be invited to join. According to this theory, we may be observed from a distance until we reach a certain level of technological or societal development. One of the most intriguing aspects of the Galactic Club hypothesis is how it intersects with human rights. If humanity were to encounter extraterrestrial civilizations with an established interstellar legal framework, we would face significant questions about whether to join that framework and how it might affect our own laws. Michael Bolander, in his article Joining the Galactic Club, What Price Admission?, explores these questions and their implications for human identity and rights. The Galactic Club would likely have its own set of rules and norms that member civilizations must adhere to. This raises the question, can there be a joint view on a global human legal position that aligns with these interstellar norms? Or is it impossible to arrive at a consensus given the diverse legal and cultural traditions on Earth? Even if we assume that we would encounter altruistic and benign extraterrestrial civilizations, their understanding of terms like altruistic and benign might differ significantly from ours. Concepts such as individualism and minority protection, which are central to many human rights regimes on Earth, might not be as important or even recognized by these civilizations. Instead, they might prioritize collective-minded frameworks or even collective consciousness. Joining the Galactic Club would involve addressing both institutional and material factors. Institutional factors include the structures and processes through which rights are protected and enforced, while material factors relate to the specific rights and freedoms themselves. Adapting our legal systems to align with the interstellar legal norms of the Galactic Club might involve significant changes to our constitution, legal codes, and judicial systems. Changes in governance structures to ensure compliance with interstellar norms could include creating new international bodies or adapting existing ones to manage our interactions with other civilizations. Ensuring accountability within this new framework would be crucial, possibly establishing new oversight bodies or adapting existing ones to monitor compliance with interstellar norms. Many human rights regimes prioritize individual rights and freedoms, such as freedom of speech, freedom of assembly, and the right to a fair trial. The Galactic Club might have different priorities, such as the collective good or the stability of the interstellar community. Human societies are characterized by a high degree of cultural diversity, which is reflected in our legal systems. The Galactic Club might require a more homogenized approach to cultural norms and practices, which could conflict with the preservation of cultural diversity on Earth. Joining the Galactic Club would likely involve adopting new technologies and practices. This could have implications for privacy rights, data protection, and the ethical use of technology. The process of negotiating membership in the Galactic Club would be complex and time-consuming. It would involve not only legal and political negotiations, but also deep ethical and philosophical discussions about the nature of humanity and our place in the universe. One of the key challenges would be reconciling human moral and ethical traditions with those of extraterrestrial civilizations. Concepts such as justice, fairness, and human dignity might have different interpretations across different civilizations. Even if extraterrestrial civilizations are altruistic and benign, their understanding of these concepts might differ from ours. They might prioritize the collective good over individual rights, or have different views on the balance between security and freedom. As Michael Bolander notes, our speculations about extraterrestrial norms and behaviors are inherently limited by our own cognitive biases. We can only extrapolate from our own history and experiences, which might not be applicable to extraterrestrial civilizations. Human rights, as currently interpreted, might not be fully compatible with the norms and rules of the Galactic Club. We would need to consider which aspects of our human rights framework are negotiable and which are non-negotiable. This would involve difficult trade-offs and ethical considerations. While the possibility of contact with extraterrestrial civilizations might seem remote, it is important to start thinking about these issues now. The process of establishing a joint legal position and negotiating membership in the Galactic Club would be long and complex. Early reflection and planning can help ensure that we are prepared for these challenges. To effectively engage with the Galactic Club, humanity would need to develop a sense of cosmic species awareness. This involves recognizing our place in the broader universe and understanding the responsibilities and opportunities that come with it. The outcomes of accession negotiations with the Galactic Club could vary widely. They would depend on the specific positions and norms of the extraterrestrial civilizations involved, as well as the nature of the issues being negotiated. It is important to keep an open mind and be prepared for a range of possible scenarios. The idea of joining the Galactic Club challenges us to think deeply about our laws, values, and identity as a species. It raises profound questions about how we would interact with extraterrestrial civilizations and what changes we would need to make to our own legal and ethical frameworks. While the prospect of contact with extraterrestrial civilizations might seem distant, preparing for these possibilities now can help ensure that humanity is ready to navigate the complex and exciting future that lies ahead. Self-destruction hypothesis. As we delve deeper into the mysteries of the cosmos, we encounter a sobering and thought-provoking theory, the self-destruction hypothesis. This idea suggests that advanced civilizations might tend to self-destruct before they can establish interstellar communication or travel. Factors such as nuclear war, environmental collapse, or technological mishaps could lead to the downfall of civilizations before they ever reach out to others. The origins of this hypothesis are rooted in the well-known Fermi Paradox, which questions why, given the vast number of stars and potentially habitable planets, we have not yet encountered any signs of extraterrestrial life. One compelling answer is that advanced civilizations may inevitably reach a point where their technological and societal advancements lead to their own destruction. Let's consider some of the potential self-destructive pathways that civilizations might follow. One of the most immediate and terrifying is nuclear war. As civilizations develop advanced technologies, they often create powerful weapons. The threat of mutual destruction could lead to catastrophic wars that wipe out entire populations, leaving no survivors to venture into space. Environmental collapse is another grim possibility. Rapid industrialization and technological growth can lead to severe environmental degradation. Pollution, deforestation, and climate change can create conditions that are no longer conducive to life. Civilizations might exhaust their planet's resources, causing ecological disasters that make survival impossible. Technological mishaps, such as accidents with artificial intelligence, could also play a significant role. As civilizations push the boundaries of artificial intelligence, they might create machines that surpass their control. An AI gone rogue could wreak havoc on a global scale, leading to the collapse of societal structures and potentially the extinction of the species. In a recent study, astrobiologists Michael Wong and Stuart Bartlett explored these ideas further. They suggested that civilizations might follow a trajectory similar to the growth patterns of cities. As cities grow, they experience increasing returns in wealth, productivity, and innovation. However, this growth can become unsustainable, leading to what they call superlinear scaling. Essentially, the demands on resources grow faster than the population, leading to inevitable collapse if unchecked. Wang and Bartlett propose that civilizations might either burn out due to unsustainable growth or transcend to a state of homeostatic awakening. In this state, civilizations recognize the unsustainability of their growth and choose to stabilize, avoiding collapse by shifting their focus away from unbounded expansion. This could mean that advanced civilizations either self-destruct or choose to remain in a stable, non-expansive state, thus explaining why we haven't detected any alien visitors. The concept of superlinear scaling is fascinating. It suggests that as civilizations grow, the time between necessary innovations to sustain growth becomes shorter and shorter. Eventually, the capacity for innovation is overwhelmed, leading to collapse. Civilizations that do not manage to reset their resource use and population trajectories face catastrophic burnout. On the other hand, those that become aware of their unsustainable trajectory might choose to transcend the pursuit of unbounded growth. This idea of homeostatic awakening means that civilizations deliberately stabilize their growth and resource consumption to maintain a sustainable existence. They might focus on creating a balanced society that does not seek endless expansion, but instead aims for long-term stability and harmony with their environment. This hypothesis offers a possible explanation for the Fermi Paradox. Civilizations either self-destruct or choose to stay quietly at home, avoiding the risks associated with interstellar travel and communication. The absence of detected alien visitors might be because those who survive do so by avoiding the pitfalls of unchecked growth and focusing on sustainable living. The self-destruction hypothesis also serves as a cautionary tale for humanity. It urges us to reflect on our own trajectory and the potential dangers of our technological and societal advancements. The challenges we face, such as climate change, nuclear proliferation, and the ethical implications of AI, mirror the potential self-destructive pathways that could have led to the downfall of other civilizations. Wang and Bartlett conclude their study with a powerful message. Understanding the dynamics that lead to superlinear growth and potential collapse might help us avoid a similar fate. By enacting fundamental changes to our way of life, we can consciously steer away from self-induced collapse and strive for a sustainable future. This hypothesis, while unsettling, provides a profound perspective on the fate of advanced civilizations. It challenges us to think critically about our own development and the choices we make. Are we on a path towards self-destruction, or can we achieve a state of homeostatic awakening? The answer might determine whether we join the ranks of civilizations that have transcended their destructive tendencies or those that have perished before reaching the stars. As we ponder these possibilities, we are reminded of the delicate balance required to sustain advanced civilizations. The self-destruction hypothesis serves as a stark reminder of the potential consequences of unchecked growth and technological advancements. It challenges us to reflect on our actions and consider the long-term implications of our choices. The post-biological hypothesis. The post-biological hypothesis presents a captivating theory about the future of advanced civilizations. This idea proposes that once civilizations reach a certain level of technological advancement, they might transition beyond their biological forms, evolving into digital or robotic entities. These post-biological civilizations could have different priorities and methods of communication that we, with our current technology, are unable to detect. Advanced civilizations might evolve in ways that transcend their biological limitations. Instead of relying on organic bodies, they could transfer their consciousness into machines or digital platforms. This transition offers numerous advantages, such as increased durability, enhanced cognitive capabilities, and the ability to exist in environments that would be hostile to biological life. The origins of this hypothesis can be traced back to various fields, including futures studies, cognitive sciences, and philosophical anthropology. The idea is that technological and cultural evolution will eventually replace the biological processes that underlie human existence. The concept can be extended to other intelligent beings in the universe, suggesting that they too might undergo a similar transformation. One of the key aspects of post-biological evolution is the concept of mind uploading. The process involves transferring an individual's consciousness into a digital substrate, preserving their thoughts, memories, and personality indefinitely. This digital existence would be free from the limitations of the human body, such as aging and disease. Another intriguing idea is cyborgization, where biological beings enhance themselves with robotic or digital components. These enhancements could include advanced prosthetics and neural implants that improve cognitive functions. As these technologies become more sophisticated, the line between biological and artificial blurs, creating beings that are part human, part machine. The notion of a technological singularity also plays a role in this hypothesis. This refers to a point in the future where technological growth becomes uncontrollable and irreversible, leading to profound changes in civilization. At this stage, artificial intelligence could surpass human intelligence, leading to the creation of beings that are vastly more advanced than we are. Astrobiologists Michael Wong and Stuart Bartlett have explored these ideas further, suggesting that civilizations might follow a trajectory where they evolve from biological to post-biological forms. This evolution could be driven by the need to overcome the limitations of biological existence and achieve greater control over their environment. Wong and Bartlett propose that post-biological civilizations might either burn out due to unsustainable growth or transcend to a state of the homeostatic awakening. In this state, they recognize the unsustainability of their growth and choose to stabilize, avoiding collapse by shifting their focus away from unbounded expansion. This could mean that advanced civilizations either self-destruct or choose to remain in a stable, non-expansive state, thus explaining why we haven't detected any alien visitors. The idea of post-biological evolution challenges our understanding of life and intelligence. It suggests that life doesn't have to be bound by organic forms. Instead, it can evolve into new, unimaginable forms that transcend the limitations of biology. These post-biological beings might exist in digital or robotic forms with vastly different priorities and methods of communication than we can comprehend. Milan M. Cirkovich, a researcher in this field, has explored the concept of post-biological evolution. This involves a kind of reintegration with the natural universe, where the products of culture become indistinguishable from the natural environment. In this scenario, the dichotomy between biological and post-biological becomes irrelevant, as advanced civilizations merge with the universe in ways that are currently beyond our understanding. Cirkovich suggests that post-biological evolution might not be the final stage. Instead, there could be a reverse trend where these advanced beings reintegrate with the natural universe, merging culture and nature seamlessly. This would mean that the distinction between biological and artificial life becomes meaningless at a certain level of advancement. This concept challenges the traditional view of evolution as a linear progression. Instead, It suggests a more complex and dynamic process where civilizations continually evolve and adapt, exploring new forms of existence. This could lead to a state where the products of culture and technology are indistinguishable from the natural environment, creating a harmonious and integrated existence. The post-biological hypothesis also raises interesting questions about the future of humanity. As we continue to develop advanced technologies, we might one day face the choice of whether to remain biological or transition to a post-biological existence. This transition could offer numerous benefits, but it also poses significant ethical and philosophical challenges. For instance, what would it mean for our identity if we were to upload our minds into a digital substrate? Would we still be the same person, or would we become something entirely new? How would our society change if we were no longer bound by the limitations of our biological bodies? These questions are not just theoretical. They have real implications for the future of humanity. The post-biological hypothesis also offers a potential solution to the Fermi Paradox. If advanced civilizations evolve into post-biological forms, they might not be interested in interstellar communication or travel. Instead, they might focus on achieving a stable, sustainable existence within their own systems. This could explain why we haven't detected any signs of extraterrestrial life. Furthermore, post-biological civilizations might have communication methods that are beyond our current capabilities to detect. They might use advanced forms of communication that are undetectable with our current technology, such as quantum entanglement or other forms of non-local interaction. This could mean that these civilizations are out there, but we simply don't have the means to perceive them. This hypothesis encourages us to expand our understanding of life and intelligence. It suggests that life, in its many forms, might be far more diverse and extraordinary than we can currently imagine. The possibilities are endless, and as we continue to explore the universe, we must remain open to the idea that there are forms of existence that transcend our current understanding. As we delve deeper into the mysteries of the cosmos, the post-biological hypothesis serves as a reminder of the potential for life to evolve in ways that are beyond our current comprehension. It challenges us to think beyond the confines of biological existence and consider the infinite possibilities that await us in the vast expanse of the universe. In conclusion, the post-biological hypothesis offers a fascinating perspective on the potential future of advanced civilizations. It suggests that life can evolve beyond its biological origins, transcending the limitations of organic existence to achieve new forms of intelligence and existence. This hypothesis challenges our understanding of life and raises profound questions about the future of humanity and our place in the cosmos. As we continue our journey through the mysteries of the universe, we must remain open to the possibility that life, in its many forms, might be far more diverse and extraordinary than we can currently imagine. The post-biological hypothesis is a reminder that the cosmos is vast and full of potential, waiting for us to explore and understand its many wonders. The ancient astronaut hypothesis. This is a fascinating and controversial theory that suggests extraterrestrial beings visited Earth in the distant past and influenced the development of human civilization. Proponents believe that ancient structures, myths, and texts contain evidence of these encounters, indicating that our ancestors had contact with advanced alien visitors. This hypothesis, often linked with the work of popular authors like Erich von Däniken and Zecharia Sitchin, proposes that intelligent extraterrestrial beings made contact with humans during antiquity and prehistoric times. These visitors, often depicted as gods or divine beings, are believed to have brought advanced technologies and knowledge that significantly impacted early human societies. The hypothesis suggests that these extraterrestrials helped shape the development of modern cultures, technologies, religions, and even human biology. One of the central claims of the ancient astronaut hypothesis is that many deities from various religions are, in fact, extraterrestrial in origin. The advanced technologies brought to Earth by these ancient astronauts were interpreted as evidence of their divine status by early humans. For instance, the construction of monumental structures like the Egyptian pyramids, the Moai stone heads of Easter Island, and Stonehenge are often cited as examples of achievements that required knowledge and technology beyond the capabilities of the civilizations of the time. Proponents argue that these structures were either directly built by these extraterrestrial visitors or constructed with their assistance. The idea that ancient astronauts existed and visited Earth is not widely accepted by mainstream academics and archaeologists. They often identify such claims as pseudo-archaeological and unscientific, pointing out that the evidence presented by proponents is frequently distorted or fabricated. Nonetheless, the theory continues to capture the imagination of many, fueled by television shows, books, and documentaries. Erich von Däniken, a leading figure in the promotion of the ancient astronaut hypothesis, gained widespread attention with his 1968 book, Chariots of the Gods. In it, he argues that certain artifacts require more sophisticated technological abilities than those available to ancient cultures. Von Däniken suggests that these artifacts were either directly constructed by extraterrestrial visitors or by humans who learned from them. He interprets ancient art and iconography from around the world as depictions of air and space vehicles, non-human intelligent creatures, and advanced technologies. Von Däniken's interpretations of various ancient texts and artifacts have been widely criticized. For example, his interpretation of the sarcophagus lid from the tomb of the Maya ruler Pakal the Great as depicting a seated astronaut is contradicted by mainstream scholars who identify it as a portrait of the ruler himself with the world tree of Maya mythology. Despite such criticisms, von Däniken's work remains influential and has inspired many to explore the possibility of ancient extraterrestrial contact. Zecharia Sitchin's series, The Earth Chronicles, beginning with the 12th planet, builds on the ancient astronaut hypothesis with a unique interpretation of ancient Sumerian and Middle Eastern texts. Sitchin hypothesizes that the gods of ancient Mesopotamia were astronauts from a planet called Nibiru. According to his theory, these extraterrestrial beings came to Earth to mine gold and created humans to serve as their laborers. Sitchin's ideas have been widely criticized by mainstream scholars, particularly his translations of ancient texts, which many argue are inconsistent with known Sumerian and Mesopotamian records. The ancient astronaut hypothesis also finds support in various mythologies and religious texts. Proponents cite ancient creation myths and stories of gods descending from the heavens as evidence of extraterrestrial visitors. For instance, the Hindu epic Ramayana mentions flying vehicles called Vimanas, which are interpreted by proponents as ancient spacecraft. Similarly, the book of Ezekiel in the Bible describes a vision of a flying chariot, which some believe is a description of an alien spacecraft. Critics argue that these interpretations often reflect a confirmation bias, where evidence is selectively interpreted to fit the hypothesis. They contend that many of the so-called out-of-place artifacts cited by proponents can be explained through conventional archaeological and historical methods. For example, the Nazca lines in Peru, which von Daniken suggested were landing strips for ancient astronauts, are now understood to be ceremonial pathways created by the Nazca culture. The ancient astronaut hypothesis has also been linked to controversial and problematic ideas, such as the belief that indigenous cultures were incapable of achieving their technological and cultural feats without extraterrestrial assistance. This perspective has been criticized for perpetuating a form of cultural erasure and undermining the achievements of ancient civilizations. Despite these criticisms, the hypothesis remains popular, particularly in popular culture. Television shows like the History Channel's Ancient Aliens continue to explore and promote the idea that extraterrestrial beings played a significant role in human history. These shows often mix fact with fiction, creating a compelling narrative that appeals to a wide audience. In conclusion, the ancient astronaut hypothesis offers a provocative perspective on the development of human civilization. While it is widely regarded as pseudoscientific by mainstream academics, it continues to inspire interest and debate. The idea that advanced extraterrestrial beings might have visited Earth and influenced our ancestors taps into a deep curiosity about our origins and our place in the universe. As we continue to explore the mysteries of our past, it is essential to approach such theories with a critical mind, evaluating the evidence and considering alternative explanations. Whether or not there is any truth to the ancient astronaut hypothesis, it undoubtedly enriches our understanding of history and fuels our imagination about the possibilities of life beyond Earth. Panspermia Hypothesis. The Panspermia Hypothesis suggests that life on Earth might have originated from microorganisms or chemical precursors of life present in outer space. According to this theory, these life forms could have been transported to Earth via comets, asteroids, or interstellar dust. While the hypothesis doesn't explain how life initially began, it addresses how life might be distributed across the galaxy. Imagine a tiny microorganism hitching a ride on a comet or an asteroid, traveling through the vast expanse of space and eventually landing on a young, hospitable Earth. This is the essence of the Panspermia hypothesis. The idea of panspermia isn't new. It dates back to the work of researchers like Jöns Jacob Berzelius, Hermann Richter, and Svante Arrhenius from the 1830s through to the early 1900s. In more recent years, it has been championed by scientists such as Professor Chandra Wickramasinghe, a former colleague of the famous cosmologist Sir Fred Hoyle. Panspermia encompasses several different ideas about how life could be spread across the universe. One version, known as lithopanspermia, proposes that extremophile-type microscopic life could exist in debris blasted into space from planetary collisions with asteroids and comets. These hardy microorganisms might then survive the journey through space and eventually land on another planet, potentially seeding life there. Another variant, radiopanspermia, suggests that organisms might travel through space via radiation pressure from stars. While the harsh environment of space, including ultraviolet and X-ray radiation, poses significant challenges, some scientists believe that a sufficient number of microorganisms could survive to seed a suitable planetary environment. Pseudopanspermia, on the other hand, posits that the organic building blocks of life originate in interstellar dust clouds and are transported to the surfaces of planets where life then develops via abiogenesis. In this scenario, the molecular precursors of life, rather than life itself, are spread through space. Despite the intriguing possibilities of panspermia, the theory has faced skepticism. One major challenge is the survival of microorganisms during space travel. The vacuum of space, extreme temperatures, and radiation are all formidable obstacles. However, some experiments have provided promising evidence. For instance, the expose experiments on the International Space Station showed that meteorite-type protection layers around organic biological samples could allow bacterial endospores and even seeds to survive in the harsh vacuum of space. From 2008 to 2016, samples exposed to space conditions were returned to Earth, and some microorganisms were found to have survived. In one case, 100% of the bacterial endospores placed in Mars-type conditions were still viable. Additionally, a quarter of the experiment's tobacco seeds survived to be grown as plants back on Earth. These findings represent the first data evidence that basic cryptoendolithic life, organisms that colonize cavities in the structures of rocks, can be hardy enough to survive movement through outer space. These results are of key importance to the panspermia debate and future exobiology research directions. They also have direct relevance to future Mars mission sample analysis, planetary protection sterilization for lander probes, and the exploration of possible life-bearing environments across the solar system and beyond. Further supporting the possibility of panspermia, there have been other experiments such as Biopan on Russian photon capsules and Exostack on the U.S. Long-Duration Exposure Facility satellite. These have shown that when given basic protection, spores, lichens, and even tiny animals known as tardigrades could survive for a few years in space. Famously, a piece of the Surveyor 3 lunar lander that was brought back to Earth by the Apollo 12 crew in 1969 was found to contain an Earth bacterium that appeared to have survived unprotected for over 2 years on the airless surface. Though this finding is controversial and could be due to laboratory contamination, it sparked further interest in the potential for microbial survival in space. The search for space microorganisms has also been conducted at stratospheric altitudes. For example, the Indian Space Research Organization carried out balloon flights between 2001 and 2006 to search for life at high altitudes. While some results were considered indicative of interplanetary cells, later studies suggested that large-scale convection could transport Earth bacteria to the upper reaches of the atmosphere, complicating the interpretation of these findings. To explore the viability of panspermia, scientists continue to conduct research on extremophiles, organisms that can survive extreme conditions, and study the composition of comets, asteroids, and interstellar dust grains. For instance, the Tanpopo mission, named after the Japanese word for dandelion, aimed to test whether bacteria could survive in the extremes of outer space. Researchers from Tokyo University, in conjunction with the Japanese National Space Agency JAXA, exposed the bacteria Deinococcus to space conditions on the exterior of the International Space Station. The results showed that the bacteria could survive, with dead outer layers protecting the inner colony. This suggests that bacteria could potentially survive the journey from Earth to Mars and vice versa, supporting the Panspermia hypothesis. The potential implications of panspermia are profound. If life can be transported between planets, it raises the possibility that life exists much more frequently in the universe than previously thought. It also suggests that Earth might not be unique in harboring life, and that life on our planet could have originated from elsewhere in the cosmos. The theory of panspermia doesn't necessarily explain the ultimate origin of life. Instead, it offers an alternative hypothesis for how life could have spread throughout the universe once it emerged. The theory raises important questions about the prevalence of life in the cosmos and the potential for life to exist beyond Earth. Critics of panspermia argue that the survival of microorganisms during space travel and their ability to colonize new environments are subject to numerous challenges. These include exposure to radiation, extreme temperatures, and the vacuum of space. However, ongoing research and experiments continue to explore these possibilities. Future space missions, such as NASA's Perseverance rover on Mars, aim to search for signs of past or present life on other planets. These missions will help scientists determine if panspermia has been operating in the solar system. If life is found on Mars or other celestial bodies and shares key biochemical characteristics with life on Earth, it would support the idea of a common origin through panspermia. Conversely, if life is found to be fundamentally different, it would suggest that life could arise independently in different environments. The Panspermia Hypothesis remains a subject of ongoing scientific investigation and debate. As we continue to explore the mysteries of our universe, the possibility that life might be more widespread than we ever imagined remains an exciting and tantalizing prospect. In conclusion, the Panspermia Hypothesis offers an intriguing perspective on the origins and distribution of life in the universe. While it faces significant challenges and skepticism, it also opens up new avenues for understanding how life might have spread across the cosmos. The search for extraterrestrial life and the exploration of our solar system will continue to shed light on this fascinating theory and its implications for our understanding of life beyond Earth. Quantum entanglement theory. Quantum entanglement theory suggests that advanced civilizations might use quantum entanglement for communication, a method that would be instantaneous and undetectable with our current technology. Quantum entanglement, once dubbed spooky action at a distance by Albert Einstein, has recently garnered significant attention, culminating in a Nobel Prize win in 2022 for demonstrating its existence and potential applications. To grasp how quantum entanglement could revolutionize communication, let's first delve into what quantum entanglement is. Imagine two particles becoming intertwined in such a way that the state of one particle instantaneously affects the state of the other, regardless of the distance separating them. This phenomenon was first proposed by Einstein, Podolsky, and Rosen in the 1930s, highlighting a curious and perplexing aspect of quantum mechanics. Despite the seemingly instantaneous interaction between entangled particles, modern science tells us that it's impossible to transmit data using quantum entanglement alone. This limitation arises because, while the particles appear to communicate instantaneously, they do not convey any usable information in a manner that we can harness for communication. However, if a breakthrough occurs, allowing us to manipulate these particles for data transmission, the implications for secure and rapid communication would be profound. The 2022 Nobel Prize in Physics recognized the work of Alain Aspect, John F. Clauser, and Anton Zeilinger, who conducted pivotal experiments with entangled photons. Their work confirmed that entangled particles could indeed remain connected over long distances, providing a foundation for future applications in quantum communication, quantum computing, and quantum cryptography. One potential application of quantum entanglement in communication is quantum key distribution. This method involves encoding information in quantum states, known as qubits, rather than traditional binary codes. Quantum key distribution leverages the unique properties of quantum states to ensure secure communication, as any attempt to intercept the data would alter the state of the qubits, revealing the presence of an eavesdropper. Currently, quantum key distribution links are limited to relatively short distances, but ongoing research into quantum repeaters and satellite quantum key distribution aims to extend this range. Although the notion of faster-than-light communication through quantum entanglement remains a topic of debate, it has sparked considerable interest and research. Quantum entanglement, while not yet enabling faster-than-light communication, has already demonstrated its potential for quantum teleportation. This process involves transferring the quantum state of one particle to another, effectively teleporting information instantaneously. While practical implementation of this technology is still in its infancy, the concept alone opens up a realm of possibilities. Chinese physicists have even measured the speed of quantum entanglement, finding that it exceeds the speed of light. However, this interaction does not yet translate into faster-than-light communication, as we currently lack the means to transmit usable data through entangled particles. Instead, the measurements serve as a proof of concept, hinting at the future potential of this phenomenon. The challenge lies in overcoming the inherent randomness of quantum measurements. In quantum entanglement, you cannot force a particle into a particular state or predetermine the outcome of a measurement. This randomness prevents the direct transmission of information. Researchers are exploring ways to manipulate entangled particles and develop protocols that could harness this phenomenon for communication. In practical terms, quantum entanglement could revolutionize cybersecurity. As quantum computing advances, traditional encryption methods will become vulnerable to new forms of cyber attacks. Quantum communication, with its inherent security features, could provide a robust defense against such threats. Government agencies worldwide are already preparing for Q-Day, the anticipated moment when quantum computers will be capable of breaking current encryption methods. By leveraging quantum entanglement, we could develop secure communication channels resistant to even the most advanced cyber threats. Quantum communication also has the potential to impact various fields, from weather prediction to medical research and artificial intelligence. Quantum computers can solve complex problems at speeds far beyond the capabilities of classical computers, offering new insights and advancements across numerous disciplines. However, the journey to practical quantum communication is still fraught with challenges. Current quantum communication methods, such as quantum key distribution, are limited by distance and require significant technological advancements to become viable for widespread use. Researchers are working on developing quantum repeaters, which could extend the range of quantum communication networks. Additionally, the integration of quantum communication with existing infrastructure, like fiber optic networks, poses technical and logistical hurdles. Despite these challenges, the potential benefits of quantum communication continue to drive research and development. Imagine a future where instantaneous secure communication is the norm, enabling real-time data exchange across vast distances without the risk of interception. Such a breakthrough could transform not only how we communicate, but also how we conduct business, govern societies, and explore the universe. In the context of extraterrestrial civilizations, quantum entanglement offers a tantalizing possibility. If advanced civilizations have mastered quantum communication, they could communicate across interstellar distances without our current technological limitations. This would explain why we have not detected any signals from such civilizations. Their communication methods might be undetectable with our existing technology. The 2022 Nobel Prize in Physics underscored the significance of quantum entanglement in the realm of quantum information science. By validating the existence and practical applications of quantum entanglement, researchers have paved the way for future advancements in quantum communication and beyond. As we continue to explore the mysteries of quantum mechanics, The dream of faster-than-light communication remains a beacon of possibility, inspiring scientists and researchers to push the boundaries of what we know and what we can achieve. In conclusion, quantum entanglement theory represents a fascinating frontier in the quest for advanced communication technologies. While we have yet to unlock the full potential of quantum entanglement for data transmission, ongoing research and groundbreaking experiments continue to illuminate the path forward. As we venture deeper into the quantum realm, the prospect of instantaneous secure communication brings us one step closer to a new technological epoch, bridging the gap between science fiction and reality. The Multiverse Theory. The Multiverse Theory suggests that there are multiple universes with different physical laws and constants. It's possible that intelligent life exists in parallel universes that we are unable to observe or interact with. Imagine the vastness of space, time, and existence, not confined to a single universe, but spread across an endless array of parallel worlds, each with its own unique set of rules. This mind-bending idea has fascinated scientists, philosophers, and even storytellers for generations. To start, let's define what the multiverse is. The multiverse is the hypothetical set of all universes, encompassing everything that exists: space, time, matter, energy, and the physical laws and constants that describe them. Within this grand structure, the different universes are referred to by many names, including parallel universes, alternate universes, and many worlds. Some scientists envision the multiverse as a patchwork quilt of separate universes, all bound by the same laws of physics. The concept of multiple universes isn't new. It has deep historical roots. The idea was first suggested by the pre-Socratic Greek philosopher Anaximander in the 6th century BCE. However, the ancient Greek atomists, such as Leucippus and Democritus, were the first to propose the existence of innumerable worlds definitively. Later, philosophers like Chrysippus and Lucretius expanded on these ideas, suggesting that the world eternally expired and regenerated, effectively hinting at the existence of multiple universes across time. Fast forward to the modern era, and the American philosopher and psychologist William James used the term multiverse in 1895, albeit in a different context. The concept took a scientific turn during the debate between physicists Ludwig Boltzmann and Ernst Zermelo in the late 19th century. In 1952, Erwin Schrödinger even joked about the idea, suggesting that different histories described by quantum equations all happen simultaneously. The scientific community has proposed various multiverse theories over the years. Max Tegmark and Brian Greene have each developed classification schemes to describe the different types of multiverses. Tegmark's classification includes 4 levels. Level 1, an extension of our universe. This level posits that if space is infinite, there must be regions beyond our observable universe that are similar or even identical to our own. Level 2, universes with different physical constants. In this scenario, cosmic inflation creates distinct bubble universes with different physical properties. Level 3, many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event spawns a new universe, leading to a branching multiverse where all possible outcomes occur. Level 4, ultimate ensemble. This level encompasses all universes that can be described by mathematical structures, suggesting that any conceivable universe exists. Brian Greene expands on these ideas with his own 9 types of multiverses, including quilted, inflationary, brane, cyclic, landscape, quantum, holographic, simulated, and ultimate multiverses. These classifications explore various dimensions of space, physical laws, and mathematical structures to explain the existence and interactions of multiple universes. One of the most intriguing aspects of the multiverse theory is its potential to explain the fine-tuning of our own universe for conscious life. The anthropic principle suggests that we exist in one of the few universes that support life. In this context, the multiverse provides a solution to the question of why the physical constants of our universe are just right for life to evolve. If there are countless universes, each with different properties, it's not surprising that at least one would have the conditions necessary for life as we know it. The multiverse theory also raises fascinating questions about the nature of reality and our place in it. Are we living in a universe that is just one of many, each with its own version of events and outcomes? This idea has profound implications for our understanding of existence and the limits of human knowledge. Despite its allure, the multiverse theory faces significant criticism from the scientific community. One major challenge is its lack of empirical testability. Critics argue that because we cannot observe or interact with other universes, the multiverse concept lacks the necessary falsifiability to be considered a scientific hypothesis. Paul Davies, a prominent cosmologist, likens the multiverse to theological discussions, suggesting that it requires a leap of faith akin to belief in an unseen creator. George Ellis, another respected physicist, points out that the multiverse lies beyond the reach of our telescopes and that it may never be possible to find empirical evidence for its existence. He emphasizes the importance of observational testing in science and cautions against accepting theories that cannot be empirically verified. In contrast, proponents like Max Tegmark argue that the multiverse is a simpler and more elegant explanation for the fine-tuning of our universe. They contend that rejecting the multiverse requires introducing unsupported processes and ad hoc postulates, making the single universe model more complicated. The debate over the multiverse theory also touches on philosophical questions about the nature of reality and existence. Modal realism, the belief that all possible worlds are as real as our own, aligns with the multiverse concept, suggesting that every conceivable scenario exists somewhere in the multiverse. This idea challenges our traditional understanding of reality and raises profound questions about the nature of existence and the limits of human perception. Historically, the idea of multiple universes has appeared in various forms. In ancient times, philosophers like Democritus and Epicurus proposed the existence of countless worlds, each with its own unique characteristics. During the Middle Ages, the concept of multiple universes became more defined, although it remained largely speculative. In the 20th century, scientific discussions about the multiverse gained prominence. Theoretical physicists like Hugh Everett and his many worlds interpretation of quantum mechanics brought the idea into the realm of modern science. According to the many worlds interpretation, every quantum event creates a branching universe, leading to an ever-expanding multiverse where all possible outcomes occur. The search for empirical evidence of the multiverse has been ongoing. In the 1990s, scientists like Stephen M. Feeney analyzed data from the Wilkinson microwave anisotropy probe and claimed to find evidence of collisions between our universe and parallel universes. However, subsequent analyses, including data from the Planck satellite, did not reveal any statistically significant evidence of such collisions. In 2015, astrophysicist Ranga Ramchari analyzed the cosmic radiation spectrum and found a signal that could potentially indicate the presence of a parallel universe. However, this finding remains a matter of debate, with a significant chance that the signal is merely noise. Despite the lack of definitive evidence, the multiverse theory continues to capture the imagination of scientists and the public alike. It offers a tantalizing explanation for the mysteries of our universe and opens up a realm of possibilities that challenge our understanding of reality. One of the most compelling arguments for the multiverse is its ability to explain the fine-tuning of our universe. The physical constants of our universe, such as the strength of gravity and the properties of fundamental particles, are precisely calibrated to allow for the existence of life. If any of these constants were even slightly different, life as we know it would not be possible. The multiverse provides a plausible explanation for this fine-tuning. If there are countless universes, each with different physical constants, it is not surprising that at least one universe would have the right conditions for life. In this context, our existence is not the result of a deliberate design, but rather the consequence of living in one of the few universes where life can arise. The multiverse theory also intersects with other major scientific concepts, such as cosmic inflation and string theory. Cosmic inflation, the rapid expansion of the universe in its earliest moments, suggests that inflation did not end uniformly across the universe. Instead, it created distinct bubble universes, each with its own set of physical laws. String theory, a theoretical framework that attempts to reconcile quantum mechanics and general relativity, also supports the idea of multiple universes. According to string theory, our universe is one of many brains floating in a higher dimensional space. These brains can interact with each other, leading to the creation of new universes through collisions. While the multiverse theory offers a compelling explanation for many aspects of our universe, it also raises significant challenges. One major issue is the lack of direct evidence. Unlike other scientific theories, which can be tested and validated through experimentation and observation, the multiverse remains largely speculative. The inability to empirically verify the existence of other universes has led some scientists to question whether the multiverse is a scientific hypothesis or a philosophical concept. Despite these challenges, the multiverse theory continues to inspire scientific inquiry and philosophical debate. It pushes the boundaries of our understanding of reality and encourages us to consider the vastness of existence beyond our own universe. Whether or not we ever find empirical evidence for the multiverse, the exploration of this idea enriches our understanding of the cosmos and our place within it. In conclusion, the multiverse theory suggests that there are multiple universes with different physical laws and constants. While it remains a topic of debate and speculation, it offers a compelling explanation for the fine-tuning of our universe and challenges our understanding of reality. As we continue to explore the mysteries of the cosmos, the possibility of a multiverse expands our horizons and invites us to imagine a universe far more vast and complex than we can currently comprehend. This theory, though controversial, has profound implications for our understanding of existence, offering a framework to explore questions about the nature of reality, the origins of the universe, and the potential for life beyond our own world. As we advance in our scientific and philosophical endeavors, the multiverse remains a fascinating and thought-provoking concept that stretches the limits of human imagination and knowledge. The multiverse theory is a captivating concept that proposes the existence of multiple universes, each with its own unique physical laws and constants. From ancient Greek philosophy to modern scientific discourse, the idea of parallel worlds has evolved and been debated across various fields. While lacking empirical evidence and facing criticism for its testability, the multiverse offers a compelling explanation for the fine-tuning of our universe and the potential for life beyond our own. As we continue to push the boundaries of scientific understanding, the multiverse theory remains a source of inspiration and intrigue, inviting us to explore the vast and mysterious cosmos in which we reside. Benevolent Overlord Hypothesis. The Benevolent Overlord Hypothesis proposes a fascinating scenario. Advanced civilizations acting as guardians or overseers of less developed civilizations like ours, subtly guiding our progress and protecting us from potentially hostile aliens until we are ready. The concept stirs the imagination, suggesting a universe teeming with life forms that may have taken it upon themselves to ensure the safety and development of younger, less advanced species. To grasp this hypothesis, we can draw on the idea that advanced extraterrestrial civilizations could be much more like us than we think. Research from the University of Oxford offers intriguing insights into this possibility. Scientists argue that aliens, like humans, might be shaped by evolutionary processes such as natural selection. This means that despite potentially vast differences in biology and environment, extraterrestrial beings could share fundamental similarities with us, having evolved to become fitter and stronger over time. The Oxford study suggests that these advanced civilizations would have undergone significant evolutionary transitions, similar to those that have occurred on Earth. For instance, just as single cells evolved into complex multicellular organisms on our planet, alien species might have experienced similar leaps in complexity. These transitions would likely lead to organisms with intricate parts working together, necessitating mechanisms to maintain cooperation and functionality. Considering this evolutionary framework, it is plausible that some of these advanced civilizations might develop a sense of responsibility towards emerging civilizations like ours. If they have experienced and survived their own stages of vulnerability and growth, they might empathize with younger species navigating similar challenges. This empathy could manifest in actions aimed at guiding and protecting us, ensuring we do not encounter hostile forces before we are capable of defending ourselves. We can all picture a galaxy where advanced beings discreetly observe developing civilizations, intervening only when necessary to prevent catastrophic encounters with malevolent extraterrestrials. These guardians might employ advanced technologies to cloak their presence, subtly influencing the trajectory of a civilization's progress. Their guidance could come in various forms, from nudging scientific discoveries in a beneficial direction to averting potential threats from other spacefaring species. One might wonder why these benevolent overlords would choose to remain hidden, rather than openly interacting with us. The answer could lie in their understanding of the importance of self-discovery and growth. Just as a parent guides a child without dictating every action, these advanced civilizations might believe that allowing us to make our own mistakes and achievements is crucial for our development. By staying in the shadows, they ensure that our evolution is driven by our own efforts, preserving the authenticity of our progress. The Oxford researchers' findings lend credence to the idea that extraterrestrial life, if it exists, would likely be complex and capable of sophisticated behaviors. The mechanisms that maintain cooperation and functionality within these organisms could extend to their societal structures, fostering a culture of guardianship and oversight. This implies that advanced civilizations might not only be technologically superior, but also possess advanced ethical frameworks guiding their interactions with less developed species. In this light, the Benevolent Overlord hypothesis offers an optimistic perspective on the Fermi Paradox, which questions why we have not yet made contact with extraterrestrial civilizations despite the high probability of their existence. Perhaps the silence and absence of direct contact are not due to a lack of life in the universe, but rather a deliberate choice by advanced beings to monitor and protect us from afar. They could be waiting for the right moment, ensuring that when contact does occur, it is under conditions that are safe and beneficial for both parties. This hypothesis also opens up a realm of possibilities for how we might eventually discover these guardians. As our own technology advances, we may develop the means to detect the subtle influences and protective measures these civilizations have in place. This discovery could revolutionize our understanding of our place in the universe, shifting our perspective from one of isolation to one of interconnectedness with a broader galactic community. Ultimately, the Benevolent Overlord hypothesis challenges us to consider the potential for advanced civilizations to act not as conquerors or indifferent observers, but as caretakers of the cosmos. It invites us to imagine a universe where compassion and stewardship are as advanced as technology, where the wisdom of older species helps to nurture the growth and development of younger ones. This vision of the future encourages us to look to the stars with hope, curiosity, and a sense of shared destiny with the myriad forms of life that might inhabit our galaxy.